For many projects it's important to know where the centre of mass is, because centre of mass has many applications. If you're building a building, for example, if the centre of mass is above the base, then it's stable. If you have a building like the Leaning Tower of Pisa, as long as it's above the base, it's going to be stable. If it gets to here though, beyond the base, falls over. Also things like if you've got a linear system, if you push through the centre of mass, through the centre of gravity, it'll go in a straight line. If you push off to one side, it'll spin. So knowing where the centre of mass is important. And if it's just a flat steel homogeneous plate or an aluminium plate, you can just, centre of mass is going to be the same as the centroid. But what happens if it's not? Let's take an example. If I have a weight, we've got a 6 kg weight, it's on a bar, the bar, say that's 0.1 metre, it's on a 0.5 metre bar, and on this end we've got an 8 kg weight, which is 0.1 as well. Where's the centre of mass in that system going to be? And we can use a system very similar to what we're using in centroids. If you haven't seen the centroids videos, I recommend you do so now. But the centre of mass is going to equal the sum of the mass times the distance over the sum of the masses. So that's equal to mass 1, distance 1, plus mass 2, distance 2, over mass 1, distance, mass 2, plus mass 2, plus mass ... So what we do is just like, this is a nice simple example, but if we would break this up into 3 areas, 1, 2, 3, we can set up one of those tables. I'm just going to find out where the x dimension is. I haven't put a y dimension. Let's just find out the centre of mass on x. So what we do, again, we do a table like we did for the centroids. So we have the number, so we've got unit 1, 2, 3. We've got the mass, so I haven't given a mass for that. Let's say the bar is 2 kg. So the mass, so again, same type of thing. We have to define where we're going to measure 0 from. Make it easy. Let's take that as 0. Okay. So we're going to take that edge as 0. It's not. So what we have is mass 1 is 6 kg. Mass 2 is 2 kg. Mass 3 is 8 kg. So the sum of the masses, remember we need the sum of the masses for that bit there, is equal to 16 kg. We then take the distances for each. Well, the centre of mass, we're going to assume that the centre of mass for each individual bit, because they're rectangles, is going to be in the centre of the rectangle. So if that's 0.1, it's halfway along, so it's 0.05. This is going to be 0.1 plus half of this distance, so 0.235. So 0.1 plus 0.25 is 0.35, and this is going to be halfway through there, so it's going to be 0.1 plus 0.5 plus half of that, so that's going to be 0.65. Then we multiply the mass times the distance. So we go 6 times that, that's going to be 0.3, 2 times 0.35 is 0.7, and 8 times 0.65 is going to be 5.2. And again, that seems reasonable because that's the biggest weight and it's the furthest from there. So this is going to equal 6.2. Therefore, to find this, the centre of mass equals the sum of mass times distance over the sum of mass. This number is the sum of mass times distance, so it's going to equal 6.2 over the sum of the mass, which is 16. Calculator time, that's what they invented, 6.2 divided by 16 equals, so the sum of mass equals 0.3875 metres from the left. So let's just draw that in. 0.5, it's a halfway along, it's 0.1, 0.35. So it's going to be just over halfway, a little bit over halfway. 0.3875 metres, and that's going to be the centre of masses. Does this seem reasonable from experience? If you have a dumbbell or something with a heavy weight on one end, a light weight on the other, it does tend to be further towards the heavy weight, so that seems perfectly consistent with reality. So now we're going to apply this, in the next video we're going to apply this to sheet metals and things when you're dealing, we're going to make it much more like a centroids problem.